Welcome back to another exciting chemistry lesson. In the previous lesson, we learned about the ideal gas equation. In this lesson, we are going to learn how to combine the two ideal gas equations that allow us to determine the initial or the final values of any variable in the two equations when there are changes to any particular variable. So let me illustrate that to you. First of all, we know this is a constant. That means it doesn't change, right? So if that's the case, we can do this. We can put, and that R is now isolated so that we can bring the number of moles and T over here. So we have PV equal to NT. Now this can be set as condition number 1, okay? And that can be equal to another condition, PV over NT. Now this is condition number 2. Well, think of 1 and 2 as initial and final, okay? So keep that in mind. And here I have this right here, initial equal to final. And that's possible because of the R constant are the same for both equations. Again, the constant doesn't change. So when we're comparing the two equations, the beauty thing about this is that any variable that are not changing and that are fixed, we don't have to include them. So we can cross them out. And as you can see them in the sample below. So let's look at this right here. We have 2 liters of oxygen gas and 1 liter of nitrogen gas, each originally at 1 atmosphere and 0 degrees Celsius. The two gases are combined in 1 liter container, okay? If the temperature is held constant, so T is constant, what is the total pressure? So first of all, we have to look at this in terms of like this, okay? So I'm going to show you everything from the very beginning. Assume that you don't remember this combined equation. So we have PV equal to nRT, okay? So again, we know this equation really well, and we can set this up that PV equal to NT, and we can do the same thing here, PV equal to NT. And keep this in mind, this is final, this is final, this is final. And this is initial, this is initial, this is initial, this is initial. But in this case, the temperature is held constant, so we can cross that out. Okay? So the mole doesn't change, so we can cross that out as well. So what we have here is basically, we have PV, and this is initial, equal to PV, this is final. And look at this right here. Initially, we have 2 liter and 1 liter, so we can combine it together. We have 2 plus 1, and then for the pressure, it is 1 atmosphere, okay? So again, they are both originally at 1 atmosphere. It doesn't change, okay? Now, what we have here is we combine them together into what? 1 liter container. So we're trying to figure out what is the new pressure going to be in this changes in volume, okay? So what we have here is this. We have P final. We don't know what is that going to be, but we know the volume is 1 liter. So the answer is going to be very easily done. We just bring this over here. So this now becomes 3, right? So what we have, 3 times 1 divided by what? So I'm just going to write out. Divided by 1. What's that going to be? Equal to 3. So the answer is 3 atmosphere. And that is all we have to do. Now let's try another question. We have a sample of gas at constant volume in a rigid container. Well, that's very important because the volume doesn't change, okay? And it's heated from 200 degree Kelvin to 600 Kelvin. Well, how do we get from 200 to 600? Well, that is 3 times, isn't it? Now, the final pressure is blank. The initial pressure, the average kinetic energy of a gas molecule, is also blank. And we have this work bank right here. So think about this. We're increasing the temperature by 3 times. So what do you think is going to happen to the kinetic energy? Well, kinetic energy is directly related to the temperature, so we can best guess that it is also triple as well. The hardest part is the pressure. What happened to the pressure? Well, you can think of this in one way, okay? So what we have here is PV equal to nRT, okay? And you can think of this in terms of, let's just look at this relationship. Okay, so what we have here is the temperature increased by 3 times. Well, if that's the case, both of them on top, we can think of this as also 3 times. But here's another way to think of in terms of the combined gas law. So this is the best way to prove it. Okay, the mathematical way to prove it is that we can, again, isolate PV over NT. And this is all initial, okay? And here we have PV equal to NT, and this is all final. So what we can do is volume can be canceled out because again, it is held constant. N can be canceled out. So what we have here is Pi over Ti. And then we have PF over TF. See that? How it cancels everything else? So to solve for the final pressure, all you have to do is bring this over here. So we have TF Pi divided by Ti. Okay? And then that's equal to P. But for right here, here's where it gets tricky because TF, what is TF equal to? Well, you think about T final is 3 times the T initial right there, right? So right there 3 times. So we can replace that. We can change that out. We can change the TF equal to 3 times Ti. See that? Now what happened to the initial temperature? Cancel out. So your final pressure is equal to 3 times the initial pressure. So you can have 3 times, but the best word is triple. And that is how you use this, combine this. Again, we have these ideas and we plug this in here, okay? So be careful with that. And that's how you use this combined gas law to answer multiple choice question or question like this to some extent. So that's how we use the ideal gas equation and combine them to have 2 separate conditions to predict what are some of the changes in the final condition or what is the values in the initial condition by basic algebra. And as always, if you have any questions, take a picture of your work, put in the form, and we will do our best to help you. And we see you next time in another exciting chemistry lesson.